right, welcome everybody. So today we're going to talk about percent dissociation. And so we're going to figure out what it is and exactly how to calculate it. So percent dissociation represents the amount of a weak acid that dissociates in water. Okay, and so remember that dissociation is when the acid loses a hydrogen to produce the hydrogen ion in water and also an anion. And so what we can do is we can take the amount that actually ionizes and divide it by the initial concentration, and then that amount will be multiplied by 100 to represent a percent. Now the amount that ionizes is equal to the amount of hydrogen that's in the water after the acid dissociates in water. It's also equal to the amount of anion that's present in the water when the water dissociates. And we've been representing that in equations as X. So generally, X represents the amount of hydrogen and the amount of anion, which are equal to each other in solution. So basically, we just need to find X. We're going to divide it by the initial concentration of the acid, and then that is going to be multiplied by 100 to get percent dissociation. So it's important to note that it generally increases as the concentration decreases. So the fewer ions that are actually present in the solution, the more water molecules there are, the more those water molecules will be able to break apart or dissociate that acid. So here we have an example problem. We can calculate the percent dissociation of acetic acid. It's 0.10 molar, and the Ka value for acetic acid is given. So the first thing we can do is write our equilibrium expression for Ka. It's going to be X squared, because remember it's the concentration of the hydrogen times the concentration of the anion, because those are the products, and since they're equimolar, they're both X, divided by the initial concentration of the acid, which is 0.10. And then Ka was given to us, so we can actually substitute that value in here. It's 1.8 times 10 to the negative fifth. And so we just need to do a little bit of algebra here. To solve for X, we would first multiply both sides of the equation by 0.10. And then to find X, we would have to take the square root of that, that value. So 0.10 times 1.8 times 10 to the negative fifth should be 1.8 times 10 to the negative sixth. And then the square root of that hit the right buttons. There we go. I get X is equal to 0.0013. So I'm going to leave two significant figures there. So this is my X value. This is the molarity of the hydrogen ions in the solution. It's also equal to the molarity of the anion in solution. That is then going to be divided by our initial concentration, 0.10, and we're going to multiply that times 100 in order to get the percentage. So I divide by 0.1, multiply by 100. And so what I get for my percent dissociation is about 1.34%. So that would be the percent dissociation of that acetic acid. And so you can see that that's very low. We could see that only about 1%, so 1 out of 100 acetic acid molecules are actually going to break apart and form ions in solution. So we see why these are called weak acids. For strong acids like hydrochloric or hydrobromic, it's 100% dissociation. So 1% is very different than that. Okay, so then on the back, we have another type of problem. It's just given to us a different way. We're still going to use what we know about equilibrium expressions, values of Ka, and right now they want us to find Ka given the concentration of the solution and the percent dissociation. So what we really need to think about is what that percent dissociation represents, right? So that 3.7% is equal to my X over my initial concentration times 100. And so we just need to do a little bit of algebra here. First, I'm going to divide both sides by 100, and then I'm going to multiply both sides by 0.1. And so we end up with X is equal to 0.0037. So if we do the algebra and solve for X, X is equal to 0.0037. So that means I have the concentration of hydrogen and I have the concentration of the anion. So if I write my expression as Ka is equal to X squared over my initial concentration, I can substitute this with 0.0037 squared and solve for Ka. And so that turns out to be 1.37 times 10 to the negative fourth would be our value for Ka for lactic acid. Okay, so another thing that we need to keep in mind is that there are acids that are polyprotic. What that means is that they have more than one hydrogen ion. Okay, they dissociate stepwise. So what that means is if I have an acid like H2SO4, both of the hydrogens aren't going to dissociate at the same time. Instead, I would have an equation that showed me the dissociation of the first hydrogen, and then I would have a second chemical equation showing me the dissociation of the second proton. And so each dissociation has its own equation, and since they have their own equation, they're also going to have their own unique value for Ka. So for example, calculate the pH and concentrations of all major species in a 0.10 molar solution of carbonic acid. So we're given two Ka values here because carbonic acid, of course, has two protons. And so first, I'm going to write the equation for each of those dissociations. So first, I have the H2CO3 in water reacting to form HCO3 with a negative charge because it lost a proton, and hydronium. In the second dissociation, I'm going to take the anion here, HCO3 minus, and we're going to take off that last proton. It donates that last proton to water to become the carbonate ion and another hydronium. Okay, so what we need to do is we need to calculate the pH and concentrations of everything. And so here's what we mean by that. We need to calculate the concentrations of hydronium. That should be hydronium. We need to calculate the concentrations of each of the anions that's present in the solution. And then looking at the Ka values, they're times 10 to the negative 7th and times 10 to the negative 11th, respectively. We're probably going to neglect X over here, and so the concentrations, the initial concentration of the acid is probably going to stay 0.1. Okay, so let me set up my Ka expression. And so for the first dissociation, Ka1 was 4.3 times 10 to the negative 7th. That's equal to X squared, which is going to represent our hydronium concentration and the concentration of HCO3 minus, our anion here, over our initial concentration, 0.10. And so if we do the math for that, then we can get the value for X, which represents our hydronium concentration and our concentration of that anion. And I get 2.07 times 10 to the negative fourth. So that represents our hydronium concentration, and it represents our concentration of anion, which is necessary to start the next problem. So in the next problem, this equation has its own unique K value, so it's 5.6 times 10 to the negative 11th equal to X squared, which we already have actually the concentration of hydronium as well. So we really just need to find X for this anion, the carbonate ion. We already have the concentration of hydronium. It's going to remain largely unchanged in this equation because the dissociation value for the second equation is so small. So really, the amount of hydronium is mostly coming from this first dissociation. And that was equal to 2.07 times 10 to the negative fourth. over the concentration of this anion, of this anion from the previous equation. And so that's, again, 2.07 times 10 to the negative fourth. Because remember, x represented both of these things, right? It represented this and this in the previous equation. So I see that here as a product, and then I see the other species here as a reactant. So they actually cancel out in this equation, and so the concentration of the carbonate ion is very small. The concentration of CO3 is going to be equal to our Ka value for this equation, 5.6 times 10 to the negative 11th. And then our hydronium concentration was equal to our HCO3 minus concentration, which was equal to 2.07 times 10 to the negative fourth. The concentration of our acid is going to stay 0.10 of the original carbonic acid. And then we just need to find the pH. And so, of course, since the hydronium concentration is 2.07 times 10 to the negative fourth, we're going to negative log that value. And we get 3.68. So that would be the concentration of each species in this dissociation, and that would be the pH. So big things to keep in mind about polyprotic acids. First off, think of it as a mixture of acids, right? Because you have the initial acid dissociating to produce this still acidic anion, and then you have that acidic anion dissociating to produce the ion with no hydrogen. So you would find the value of x the same way we've been doing, use the Ka equation. When you find x, it represents the concentrations of both of these species, which then have to be substituted into the next equation. I mean, the concentration of H3O plus is going to get dropped into this equation. The concentration of HCO3 minus is going to get dropped in as the concentration of the acid in this equation. And so you'll notice sometimes that they cancel out, and so finding x is actually very, very easy. Just keep in mind what you have already and plug those things into the equation where they belong. And then finding x should be a very simple process.